Okay, folks, in this video lesson, we are going to derive an expression for the net force on a current semicircle, which would be resting in a magnetic field. So we are going to extend some of the physics that we learned in this unit. We learned that a magnetic field will exert a force on a segment of wire, and it can push that wire. Of course, the requirement is that the wire needs to be crossing magnetic field lines. So we've already done some examples with straight wire segments. In this example, we're going to actually look at what happens if the wire is curved. So what you'll want to do is to make a sketch of a semicircle, and that semicircle is, you can think of that as a wire that's being bent, and that wire is going to carry a current I, and in our picture here that current is going to be traveling in the counterclockwise direction. The radius of that semicircle is uppercase R, and we're not going to worry about the rest of the circuit here. Obviously you would need a potential difference to cause this current, etc. But we're just going to focus on the semicircle of wire. Okay. All right. Well, let's specify the direction of the magnetic field, which is coming from the outside, and we're going to say that that field is going to be coming out at us. I'm only going to draw one symbol for the magnetic field direction. I'm not going to actually be putting in other dots in this picture. So you just have to keep in mind that the magnetic field is universally, it's uniform throughout this picture. Okay, so that's what's going to be actually affecting the loop itself. So the way to handle this problem is to actually look at the arc and break it into really small pieces. So we're going to focus on a very small section of the arc here, and if you make that section, calculus small, you can kind of assume that it's going to be a little straight line segment. Okay, so this is going to be the dl that we use when we find the force on the wire. Okay, so I'm going to label that. So that's my dl, and we know now that dl actually has a direction that gets associated with it. The direction of that segment is kind of hard to draw here, but the direction would be in the same direction as the current itself. Okay, so that's what we're going to focus on here. So what I want you to do is to kind of, in your mind's eye, I want you to zoom in. Imagine that there's a small wire there, and that wire is carrying a current which is going tangent to the circle in the direction of that arrow. And in the meantime, there's a magnetic field which is pointing out. Okay, so at this point you have to use the right-hand rule, because we want to find out what's the direction of the force on that little segment. And so what you're going to do is you're going to put your fingers in the direction of dl. All right, so they go that way. And you want the palm of your hand to be facing up, because that's the direction of the magnetic field. And you'll find out that the direction of the force is going to be basically pointing radially outwards from that point. So notice that my thumb is like continuing the radius. That's actually going to be the direction of the force. Now I'm going to label that with a df, because really that force is just the force that corresponds to that very small piece. Okay, so it's not the entire force on the loop, it's only a small bit. But that's what it would be. Okay, so we've used the right-hand rule. We figured out that the force at that point is going to be going that way. Now, before we get into the mathematics of finishing the problem, I'd like you to just predict what our solution is going to look like. I hope that you can agree that as we go around to different points on this arc, that the force that we get for each piece is going to be pointing basically, away from the center of the circle. In other words, all those forces are going to be radial, directed from the center of the circle away from that. Now, the other thing I hope that you're starting to see is that if you take all those forces and you add them together as vectors, that their x components, that is the horizontal components, are going to cancel each other out, because all the forces which act on the right side of the loop are going to have a component which points to the right, and all the forces which act on the left side of the loop will have an x component which points to the left. So we would expect that there will be no net horizontal force on this loop after we finish the problem. In the vertical direction, however, we would expect that there should be a net force that results, and that's because every single vector that you draw in here has an upwards component to it. So there should be some net upwards force. Okay, so that's what we would expect to get when we complete the integration on the problem. Okay. Now, to do the rest of the integration, we have to actually specify some additional parameters here. We're going to indicate an angle theta right here, and theta is going to be the angle that the radius makes with respect to the horizontal. Okay, so that is important. Once we can put this theta in place, we can now break df into its components. We can break it into an fx component, and we can break it into a y component, dfy. And we know that the angle here is still theta because that is another interior angle in the picture. So that's the same theta. Okay. All right. So now here comes the calculus part of this. Okay. We have to do an integration over a vector quantity. We know that the magnetic force is given by a cross product. Okay. And what I've done is I've written that cross product in terms of the differential quantities, df and dl. Otherwise, it should look familiar to you, right? Magnetic force is equal to I times L cross B. We've simply replaced F and L with df and dl. Okay. In this particular problem, the angle between dl and B is always 90 degrees. I hope you can tell that from the picture. The magnetic field is always perpendicular to dl. Therefore, we can basically say that the magnitude of this df is going to be given by I times dl times B. And the sine of theta is the sine of 90, so that just kind of drops out. Okay. All right. So now we have to break this into components. So we're going to recognize that the total force, the force that we want to get, this is the net force, right? F net. It's really going to be the combination of Fx in the I hat direction plus Fy in the j hat direction. Okay. And we are going to have to do an integral to get Fx, and then we'll do another integral to get Fy. All right, and that's the calculus part. Now, remember, we know that Fx should be integrating to 0, so this integral should be like just going to 0. But the Fy should give us something that's not 0. Okay, so that's kind of the grand strategy of what we're going to do here. The remaining steps I'm going to show you are just going to be the details. So we're going to try to get this and show it's equal to 0. And then we're going to get this, and that's going to be our final answer. Okay, so we're just going to do that by doing two simple integrals. Okay, so in the x direction, to find the force, you would integrate and basically add up all of the x component force vectors from that picture that we drew. Okay. So that would be integrating times I dl b. We have to add another term here, though, because this is in the x direction. We have to add cos theta. Okay. I remind you, looking back at our picture, that this dfx in the picture is really going to be given by df times the cos of theta. Therefore, here's your df, right? And that cos theta is what we need to tack on in order to make that the x component. Okay, so that is necessary to put that cos theta in there. The other thing we're going to do is a little substitution here. We're going to not integrate in terms of the dl, but we are going to integrate instead in terms of theta. So we're going to do a replacement here. We'll circle dl, and I hope you can recognize from your knowledge of math that dl is an arc length. So an equivalent way of getting the arc length is to take the radius times d theta. Okay. So again, coming back to our picture, there's your dl, which is just a little piece of the arc, and my d theta would actually be kind of like, it's hard to show, it's very small, but my d theta would just be that little angle that corresponds to that arc. And as soon as I put it in these terms, I've now made my integral in terms of theta. I hope you can see that my theta ranges from 0 to pi because of the arc that I have. And so I can go with this. I can factor out I times r times b. I is a constant, b is a constant. Also the radius is a constant because this is a semicircle. That goes from 0 to pi, cos theta, d theta. And if you remember your trigonometry, the integral of the cosine function from 0 to pi actually is 0. That's because of the shape of the cosine function. You can prove that to yourself by sketching a cosine, right? So that's 0 degrees, that's pi radians. So this whole thing just becomes 0. And we know that there is no field in the x component. Okay, so we knew that. We kind of expected that to be the case. Okay. By the way, you could also say that's by symmetry, an argument we've made before. Okay. All right, let's proceed in the exact same way with the y force. I'm going to talk less on this because the setup is the same. The net force in the y direction is the integral of dfy. This is given by integral of I dlb sine theta. We do a substitution from 0 to pi, the integral of I r d theta b sine theta. The constants come out. I r b integral 0 to pi sine theta d theta. And I'm going to leave it to you to show that that integral is in fact not equal to 0. Okay, I'm not going to show the couple steps in here, but this would be an excellent exercise for you. You need to be able to integrate the sine function, but you can show yourself that upon evaluating that integral, you get a factor of +2. So you might want to pause the video at this point and insert the 2 or 3 steps that you need to show that that integral is +2. Okay. So at the end of the day, what you get is that the force in the y direction is equal to 2IRB. Okay. And that, of course, is an upwards force. That's its direction. And that is the basically the answer to our problem. So we've solved it. the net force is equal to 0 in the I hat direction plus 2I RB in the j hat direction. And that is what we wanted to get. So the last thing I'll just comment on is that what's kind of interesting about the solution and the problem is that you can get the exact same force on this semicircle by simply replacing it with a wire that has a length equal to 2r. So in other words, if this is your semicircle of radius r, the net force on that semicircle, is that upwards force, which is equal to 2I RB, right? The exact same force would act on a segment of wire which has a length of 2r, and that will feel the exact same upwards force. Okay, so it's kind of interesting that you can substitute a straight segment for the circular segment as well. Okay, and again, there is no x component to the force on a straight segment which is aligned in that direction. Remember, the magnetic field again is coming out at you, so so that's kind of the interesting result with this particular problem. And I leave it to you to consider whether or not you think that any arbitrary shape connecting these 2 points from here to here, from 0 to 2r, would have the same upwards force if it was connected by a wire. I'm not going to answer that, but I'll let you think about that. And I think that brings us to the end of the derivation. Okay, so I would expect that you guys can actually derive this on your own and explain your steps and apply the necessary calculus to get an answer. All right, see you soon.